Good day, everybody. I'm Simon Goldenberg, and we're going to be talking today about computing things efficiently, specifically about polynomials. How long it takes a computer program to run through its data is a very important question in computer science, particularly as the data gets bigger and bigger. Sometimes it takes a lot longer than you think. For example, if you're running a report with data about people, and it takes you 1 second to generate one person's line in the report, that's fine if you're doing a couple hundred or a couple thousand people. When you get into the millions, this starts taking a lot of time. For example, if you're running through data on the entire population of Canada, 33 million people, that's going to take you over a year at 1 second per record. So either you find a more efficient way to do it, or you explain to your client that this is what it's going to take. But usually you find a more efficient way. Database folks are really good at finding more efficient ways about this sort of calculation. But to our specifics, let's talk about polynomials. Don't worry, I'm not going to take you back to high school. I'm not going to make you solve anything. We're just going to be counting the numbers of operations, the number of multiplications and additions it takes to figure out what value this polynomial has, assuming we know values for the constants a, b, c, d, and the value x. So we've got this polynomial, constant a times x cubed plus another constant b times x squared plus another constant c times x plus a constant d. So if we have values for the constants and for the variable, how much work will a computer have to do to figure out what the end result is? And that computer can be us. So if we start with the cubic term, the highest order term, ax cubed, in order to evaluate it, we'll take x and multiply it by itself. That gets us the value of x squared. We take that value, multiply it by the x value. That gets us the value of x cubed. And then finally, we multiply it by the constant a. And that's the result of this term. 1, 2, 3 multiplications. So we've got 3 multiplications for that term. And let's put that up on the multiplication scoreboard, 3 multiplications for the cubic term. Moving on to the squared term, bx squared, we multiply the value of x times itself. That gets us the value of x squared, times b gets us the value of the term. And we're done, 2 multiplications. Put that on the scoreboard, calculate for the linear term. It's just 1 multiplication, the coefficient times x. 1 multiplication, and we're done. There are no multiplications for the constant term because there are no powers of x here. So the total number of multiplications is 3 plus 2 plus 1 plus 0, and that's 6. The number of additions we can see right away. 1, 2, 3 plus signs, 3 additions. We're adding the cubic term to the squared term. We're adding that result to the linear term, and then that result to the constant term. And I know for strict addition and strict multiplication, the order doesn't matter, but this counts how many that we have. So we've got 6 multiplications, 3 additions, a total of 9 operations for a cubic polynomial. How many more operations do we have if we make the polynomial larger? Well, let's see. If we add a 4th power term, constant k times x to the 4th, that will, as we've discussed, bring us 4 multiplications and 1 more addition. So a total of 14 operations. Now that we've got a pattern, let's see if we can do this for a polynomial of any size. We'll call it nth order, for n being whatever number you like. So let's write that down. And because we don't know how many terms we're going to have, we've got to run out of letters. Let me use the letter a for all the coefficients, and then a subscript to indicate which power they belong to. So a sub n for the nth power, a sub n minus 1 for the n minus 1st power, a sub 2 for the squared term, a sub 1 for the linear term, a 0 for the constant term. We know that each term has the same number of multiplications as the power. So our total number of multiplications is n plus n minus 1, and so forth, plus 2 plus 1 plus 0. It turns out this sum of consecutive integers has a really simple formula for the end result for any value n. And I'll link to a video that shows how that was discovered by a mathematician named Carl Friedrich Gauss when he was really young in the early 18th century. Gauss is all over the place in computing and mathematics and sciences. The end result of this sum of n, n minus 1, and so forth is the quantity n squared over 2 plus the quantity n over 2. So if I said, oh, how many multiplications there are in a polynomial of order 60, you could figure that out right away without having to add everything up. The number of additions is just the number of terms in the polynomial, so it's n, right? It's the order of the polynomial. So our total number of operations is n squared over 2 plus the quantity 3n over 2. Normally in these calculations, we don't care about the exact coefficients of the number of operations. We care more about the order, and this is of order n squared. That means as things get big, as the data set gets big, the number of operations gets bigger really fast. And here's an example. Here's a table that shows polynomial order and the number of operations from this formula. We did the case for 3 and 4, and as you see, as you go from 3 to 6, you go from 9 operations to 27. So you've doubled your size of your problem, and the amount of work you have to do goes up by 3 times. That's much faster. You get to really big polynomials like 50 terms, it's over 1,000 calculations. 100th order polynomial, it's over 5,000. That's a lot. Now, you may never encounter polynomials that big, but they are used in certain kinds of calculations and simulations, so they do happen. And if this was all there was to it, if this was just the only way to calculate polynomials, then that would be the end of the story. That if you were going to have to calculate a 50-order polynomial, it would take you 1,325 calculations to do it. But it turns out there's a more efficient way to come to the same calculation, and I'll show you that next. Let's go back to our same third-order polynomial, ax cubed plus bx squared plus cx plus d, but let's calculate it a little bit different way. Let's start out by taking the leading coefficient a, multiplying it by x, and then adding the next coefficient b. That's one multiplication, one addition. To hang some numbers on this, let's pick some really easy numbers. X equals 3, and the coefficients are 2, 4, 6, and 8, because I can calculate those in my head. So leading coefficient of 2 times x equals 3, that's 6. 6 plus 4 is 10. So this chunk of calculation is 10. And it cost us one multiplication, one addition. Okay, Simon, fine. Not sure where you're going with this, but okay. Let's carry on to the next step. Let's take the value we calculated before, multiply it by x again, and add the next coefficient, c. If you carry through the arithmetic symbolically, you've got ax squared plus bx plus c, which looks very much like this part of the polynomial here. So maybe now you see where I'm going with this. And this cost us a total of 2 multiplications and 2 additions. And what's the value? Well, we take the 10 we had last time, we multiply it by x, which is 3, that gives us 30. We add 6 to 30, and we got 36. So we're most of the way through the calculation, we know what the value is, and it cost us 2 multiplications and 2 additions total. To finish up, we take the value we calculated last time, multiply it by x again, and add d. If you carry through the symbolic multiplication, you get the polynomial back. So this is indeed the same thing arithmetically, but by calculating it this way, it cost us 3 multiplications and 3 additions total. And it's worth noting that 3 is the order of the polynomial. If we added a 4th order term, an x to the 4th term, we would just add 1 more multiplication and 1 more addition. So this method of calculating polynomials is order 2n versus the more traditional way, which is order n squared. And to fill in the numbers, we take the 36 from last time, multiply by x equals 3, that's 108, plus 8 for the constant term, 116. And you can plug that in your calculators. It should come out the same unless I made a mistake in my own arithmetic. Here's our table again that shows us the advantage of this 2n order approach versus n squared. You get a slight advantage for a 2nd order polynomial. So as soon as you go to quadratics, you've got an advantage this way. That's really interesting. When you get to the big polynomials, it's huge. For a 100th order polynomial, you're down to 200 operations from over 5,000, 96% advantage. You may not encounter these polynomials every day, but this just shows you that there can be a much more efficient way of doing things. This approach to calculating polynomials was presented to me in graduate school and called speedometer order, because it's just so much faster than doing things. So the tactical lesson is if you're ever working with polynomials in a program, write them this way, like we have on the left-hand side of the equal sign, not the more traditional way on the right. It's very much faster. This is also a great opportunity for optimizing compilers to take this form and chunk into that form to make it quicker. The more strategic lesson is that you need to try to find more efficient ways of doing things, and if you can't find a more efficient way of calculating as problems get large, let everybody know that, sorry boss, that report's going to take a year. But let me leave you with an extra fact. This approach to calculating polynomials is used in a math technique called synthetic division. And there are lots of videos. I'm not on YouTube. I'm going to link to one in the description. It's a way of calculating the values of and ultimately solving polynomials using pencil and paper. You might need a calculator if the numbers get really big or if it's funky fractions or stuff, but you can largely do it on paper because it's so much more efficient than calculating it the traditional way. And as you watch this video on synthetic division or any of the others, they're not going to tell you you're using this algorithm, but if you pay attention, you actually are. You're taking the value that you had before, multiplying by x, adding b, and then repeating, taking that value, multiplying by x, adding the next constant, the next coefficient, until you're done. There are also some very fun theorems about solving polynomials with integer coefficients that they mentioned. It gives you a bunch of solutions, and with this synthetic division approach, you can really make progress for solving any given polynomial just with pencil and paper, so that's a very cool technique. So to sum up, tactically, if you're working with polynomials, write them in speedometer order in your programs. Strategically, figure out how long your program is going to take to run as your data gets larger, and try to find more efficiencies. So thank you for your time. Please leave any respectful questions or comments in the comments section, and have a good day.